my name is Dr. Rajesh Prasad. I'm working as professor in CSA department, AKGEC, Ghaziabad. So today I'm going to talk about binomial heaps and its operation. So actually what is binomial heap? Binomial heap is actually a collection of binomial trees. So again question will come that what is binomial tree? And next one is why it is binomial. Everybody know the binomial properties like NCR and binomial theorem. So actually this kind of tree is related with this type of properties. You will see that so this follows NCR property. So that's why its name is binomial heap. And second thing, it is having mergeable heap operation. So it can merge so many heaps together. So we have so many operations, and all of them they can be merged. And this follows the minimum heap property. It's not like maximum heap property. This follows the minimum heap property. So let us since binomial heap actually is nothing but it is collection of binomial trees. So let us define the binomial tree. So the binomial tree BK is an ordered tree, right? So which is defined recursively. B0 consists of a single node. Like B0, if we talk about B0, this consists of a single node, right? And now BK consists of two binomial trees, BK minus 1, linked together. Root of one is the leftmost child of the root of the other. So if we are talking about binomial tree of order K, so this BK is nothing but it is defined recursively, BK minus 1 and BK minus 1. Root of one is left child of other. See this? Root of one is the leftmost child of the root of the other. So this is how it is defined. BK is nothing but collection of 2 BK minus 1. So B0 is one node, and let's say B1. If we define B1 is nothing but collection of 2 B0. One is leftmost child of other, and B0 is a single node. So this is single node and this is single node. Since there are no other child, so we can write this equal to this. So this is B1 actually. So similarly, if we talk about B2 is collection of 2 B1, right? So this 2 B1, clear? Yes. So now this B1, again B1 is collection of 2 B0. So this B1 is replaced by 2 B0 and this remain as it is, and B1 is replaced by 2 B0. So this is actually, this follows this structure. So this is your B2. So this is B2, right? So similarly, if we talk about B3, so this is collection of 2B2. This is collection of 2B2, right? So, and again this B2 is nothing but like see, this is collection of B3 is collection of 2B2, right? And now if we go and compute B2 again, so B2 is collection of 2B1 and this B2 is collection of this 2B1. Again B1, if you talk about B1, again B1 is collection of 2B0. So this is shifting here. And again B1 is collection of 2B0, right? And then again B1 is collection of 2B0. And this B1 is collection of 2B0. So this is actually the definition of binomial tree. So look at here, this same thing. B0 is single node, B1 is this, and B2 is defined as collection of 2, B1. So what are the properties of the binomial tree, right? For the binomial tree BK, there are 2 to the power k nodes. You have seen that if you are talking about B3, So B3 is nothing but this is the one. B3 is nothing but defined like this, right? So B3, there are like, if we talk about B3, so there are to the power 3 nodes. Yes, there are to the power 3 means 8 nodes. Yes, correct. This is true. There are, the height of tree is K. Yes, its depth, if you talk about depth, it's 0, 1 and 2 and it's 3. So maximum depth is 3. So therefore height of the tree is actually 3. This can be proved by the induction. And next is there are exactly KCI nodes at depth I. Exactly KCI. So if you look at here, 3C0, 3C1 node and 3C2 node and 3C3 node. It is true that at depth I, you have like here 3C0 factorial, 3 divided by 0 factorial and 3 minus 0 factorial, it is 1. So at depth 0, there is exactly one node. Same thing if you talk about 3C1, this is 3, yes, 3 nodes. 3C2 is also 3 and 3C3 is also 1. Yes. So this is true. There are 2 to the power K node. It is true. The height of tree is K. True. There are exactly KCI node. It is also true. Fourth property is this saying that the root has degree K. Yes, its degree is 3. Look at here. Number of children are 3. So if you talk about B3, its degree is 3. It has 3 children. Degree of any other node, if the children of the on the other hand, if the children of the root are numbered from left to right as K minus 1, like C, this is B2, this is B1, this is B0. Yes, so this is B3 actually. So if you talk about B3 is nothing but this is B0 and then B1 and then B2. So this is what it is saying, that if you number the children from left to right, so this is like root of the B2, this is root of the B2 and this is root of B1, this is root of B0. So this is the common property of the binomial tree, right? So this is how we are done. B0 single, BK minus 1. So I have seen it already, that 0, then 1, then 2, then 3, then 4, right? So this can be proved actually. This theorem can be proved by induction. So if you talk about theorem number 1, right? So there are exactly 2 to the power K node, right? So this can be, suppose that this is BK, right? And BK is nothing but collection of 2 BK minus 1. And by induction, suppose that this is true for K minus 1. That means there are exactly 2 to the power K minus 1 node, because it is true for K minus 1. So by this statement, you will see that in BK minus 1, there are exactly 2 to the power K minus 1 nodes. And if you see BK is actually one more than in BK. See this, 2 to the power K minus 1 and this is also 2 to the power K minus 1. So if you add this together, so this is 2 to the power 2K minus 1. So this is 2 to the power K. Because BK is nothing but collection up to BK minus 1, and we assume that number of node in K minus 1 is this, number of node in K minus 1 is this. So if you add the total number of node, you will get that this is equal to 2 to the power K. So this is okay. So number 2 is saying the height of tree is K. Suppose if you talk about BK minus 1, suppose height of tree in BK minus 1 is K minus 1, which is true. So, and you know that BK height is actually 1 plus height of BK minus 1. Height of BK minus 1. Yes. So bk means 1 plus height of bk minus 1 is k minus 1. It is making equal to k, which is true, right? Yes. So this is also correct. There are exactly kci node at depth I. You see. So in general, if you see, we assume that there are k minus 1 ci node at depth I. I ranges from 0 to k, right? So if look at here, and number of node at depth I, see, I is ranging from 0 to k, 0, 1 to k. So what are there are exactly, so if you see, if we assume that dki is total number of node at depth I, so this is total, this is actually collection of dk minus 1, right, at depth I, right, plus, you see, dki, number of node at ith level is nothing but dk minus 1 at ith level plus dk minus 1 at I minus 1 level, right? So the number of node at I minus 1 is k minus 1 ci plus, right, this is 1, and k minus 1 ci minus 1, and if you add it, it will be equal to kci. So this is also true. So number 4 is the root has degree k. Yes, this is but obvious because root has degree k. So if you talk about bk minus 1, so bk minus 1 has degree k minus 1, and its parent is having one more degree than the child. So this k minus 1 plus 1 will become k, which is true, right? And next is observation. By definition, it is already clear that bk is collection of bk minus 1. So this is clear, right? So, as I said that, let us define, now we know the binomial tree. So let us define the binomial heap, right? So what is binomial heap? Is actually set of binomial tree. We can say that this is collection of binomial tree that satisfies the following binomial heap property. Number 1 and number 2. Each binomial tree in H is minimum heap ordered. So the key of node is greater than the key of parent. Yes. Root of each binomial tree in H contains the smallest key in the tree. That is what we call it minimum heap order, right? Yeah. So second point, there is at most one binomial tree in H whose root has a given degree. So you cannot have more than one binomial tree whose degree is more than k. Like see this. Suppose this we are talking about this. This is B0, this is B1. This is collection. So this is B0, this is B1. So now this is binomial heap. And let's say 2, then 1, and then this is 6. It is true. But if you talk about see here 1 and 6 and then 2 and 5, this is not a binomial heap. Clear? Because you have this is B0, but this is B1 and this is B1. So we cannot have more than one B1 actually. So this is violating the property of the binomial heap. Second thing, once you write B0, then next one is either B1, B2 or something. You cannot have B0, then see B1, then let's say this is B3. So after B3, you cannot write B2. You know that this is not ordered tree. So see here, if we talk about 2 and then 4 and 6, then you cannot write you see, you can write 6, 7, this you can say 8, 9, and then 10. This can be like this can be like this. So this is B0, this is B1, and this is B3. So next cannot be B2, it should be more than B3. That is the implication. So So consider a binomial heap with n equal to 13. So there is logic behind this. Binary representation of 13 is actually 1101. This is binary representation of the 13. Its meaning is that if you have 13 nodes in a binomial heap, you will see that B0 is present and B1 and this is B2, this is B3. That means that B0 is present but B1 is absent, B2 is present and B3 is present, right? So that means from this, if you have 13 nodes, you cannot see B1. So you have to write B0, this is B0, and then next one is like one is missing, then B2 is present, and then B3 is present, right? So this is actually the property of the binomial heap. From the number itself, you can see which tree is present, which tree is not present. Clear? So, and this is the representation and of the binomial heaps. If you look at here, 10. So this is head of the node, head of the tree heap. You start from 10 and then this is how it is going to be done. Actually in binomial heap, each node is having the following key. This is like if we talk about X is a binomial heap. So this is parent node, parent of particular X, right? And after parent node, you are going to talk about key of the node, right? So this is parent node, which is nil, and this is key. And after key, you are writing its degree. It's a degree. This is degree, right? Next is degree. And this is pointer to left child, and this is pointer to right child, right? So right child is nothing but is a sibling. This is actually pointer to sibling, and this is pointer to left child. So any key in a binomial heap is having these operations: pointer to X, key X, degree of particular X, and pointer to left child and pointer to right child. Look at here. See this 10, yes, its parent is nil, key is 10, it has 0 degree, yes, and its left child is missing, and this is the right sibling. There is no concept of right child in the binomial heap. So this is right, see. So same thing, if you go here 1, yes, its parent is missing 1, then its degree is 2, yes, its degree is 2. This is pointer to left child and this is pointer to sibling. And you see 12 has like its 12 has parent as 1. So this is 1. Then it's 1. It's like its degree is 1. 12 has 1 degree. Yes. Then pointer to left and this is pointer to sibling. So you can reach this sibling via this only. You cannot reach this sibling from the parent directly. You have to go via this and you have to connect via the sibling. So this is the representation of the binomial heap, right? So one more important property of this is like binary representation has maximum these bits, right? So if you talk about binary representation, maximum number of bit log 2n plus 1 bit, right? Suppose you have like 15, if you have 15 node, right? So 15 nodes, so this is log 2 15 plus 1. So log 2 15, this is like 16, 16 is 4, so this is less than 4, so this is 3 plus 1. So maximum like 4 bit you can have to represent the like binomial heap with 15 nodes. So 4 bit will be required to represent the binomial heap with 15 nodes. So this was like the introduction of the binomial heap. You have seen the representation. So why we prefer binomial heap? There is reason behind preferring the binomial heap. Actually, so this is good data structure for retrieval and maintaining the key. So first one, if you want to create, you see there are 4 operations in any of the mergeable heap operation. We'll see that two mergeable heaps, binomial heap and Fibonacci heap. Both have the same number of operations, right? See, number one, if you talk about creating a new binomial heap, let's talk about creating a new binomial heap. So actually it is not doing anything. It is just creating a space. So this will just create a space for the node, right? Create a space for the node X. So what are the, how many space will be created? This is the one, like this parent field is going to be created, right? And this is like key of X is going to be created. And this is degree of X is going to be created, and this is pointer to left child and pointer to sibling. So a space is created for all the informations actually. So this is the number one operation. Allocate H, head H will be nil because there are no items. So head H will be nil. So its running time is θ1 because it is a constant. So number 2 is finding the minimum key. It is very easy operation. Suppose you have a binomial heap, let's say 2, 3 and 1 and 5, right, 7 and 8. And let's say this is 0 and 9 and let's say 10 and let's say 20, right, and let's say this is 30 and this is 40. And let's say this is 50 and this is 60, right? So suppose you are having this binomial here, and this is head of the H. So we know that minimum key will always reside on the root of the tree, root of the heap, because this is obeying the minimum heap property, right? So if you are talking about minimum key from here, definitely we know that this is the minimum key. So what you should do, Y is nil, X is head up. We start from here and we assume that minimum is infinity. Suppose that minimum is infinity, where infinity is not any key already present in the heap, right? So while X is not nil, yes. If key X, look at here, key X is 4. Yes, 4 is less than infinity, correct? So now your minimum is 4. You see, then minimum is key X and Y is going to be here. Y is pointed, Y was nil initially, Y is pointed here and X is going to be moved to the sibling of X. Now X is here. So 2 again less than 4, yes, 2 less than 4. So Y is here and X is moved to the sibling of this, right? Again 1 is less than 2, Y will be moved here and X is moved to the sibling here, right? So same thing here, again, so X is here, so its key is 0 less than 1, yes, correct. So minimum is 0 and X is going to be sibling, which sibling is nil. So we are done, because while X is not null, it is going to be executed. So minimum is going to be 0 from this truth. So what is running time? You have to see all the individual binomial trees in the binomial heap. So how many individual binomial trees are there? Log n plus 1. So maximum number of tree you are going to visit is log n base 2 plus 1, which is approximated to log n base 2. That is why it is preferred to, if you can maintain the minimum key, so minimum heap, and you see, and you can find out a minimum key in any binomial heap in log n time. So next operation is uniting two binomial heap, right? This algorithm is a quite big one, but it's very systematic, right? It has two parts, this and another part is like algorithm. So let us have one example and then we'll be back to explain this union algorithm. So generally, this, let us have one example. This is one binomial heap. You see here, this is B0 and this is B1 and this is B2. Same thing, B0, B1 and B4. So first operation in binomial heap union is to merge them together. Merging is the same. You can use the merging operation. B0, then B0, yes, 12 and 18. Then B1 and B1, 725, 337. And then B2 and then B4. So this is how after merging you are getting this. Of course, this is not a binomial heap because B0 and B0 is repeated. See this? This B0 is repeated and same thing is B1 and B1. So this is not a binomial heap actually. So what we are going to do? There are 4 cases for this. Case number 1, case number 2, case number 3 and case number 4. But no need to remember this. It is very easy. See this. After this you are starting from here. You start from X and this is definitely sibling X. Sibling X we call it next X, right? So actually next X is nothing but a sibling of X. Sibling of X. So and this guy is sibling of X, right? So what you should do, you start from here. Look at here, this X, this one, it has the same degree and this has different degree, right? So this has different degree. So what you should do, you just combine them together. So case number 3, just combine them together because this has the same degree, this has different degree. So if you combine these 2 things together, one will be root and other will be the child. So 12 and 18, if you combine this, 12 will become root and 18 will become child because it has to follow the minimum heap property. So this is case number 3. That if X, case number 3, if degree of X is equal to degree of next X. If this has degree X and definitely this sibling of next X is not equal and degree of sibling of next X is not same, then you are going to combine with case number 3. So this is how it is going to be done. This is case number 3. Now look at here. This is X and this is next X and this is sibling of next X. Sibling of next X. So all these 3 have the same degree, right? If 3 have the same degree, then case 2 will be applicable and in this situation there is a shifting. X will go here and next X will go here because you cannot combine these 2 together, otherwise it will violate the property of the binomial heap, right? So this case 2 is simple, that X and next X and sibling of next X, right? This all 3 they have the same degree. Then case 2 is applicable. Action is very simple. There is a paradigm shift. X is going to be next X and the next X is automatically shifted. So this is situation. See this here? Yeah. Now this X and next X and the sibling of next X, they have the different degree, right? Since they have the different degree, okay, so what you should do, check which one is going to be parent of other. Now next X is going to be parent. So this we call it case number 4. Right? Case number 3 was X is parent. Case number 4 is next X is parent. So it's very simple. Once this is going to be connected here, so 7 and 25 will be here. Right? Yes. So now 7 and 25 is here. 12, 18 and this is true actually. So class, so you are here X and this is next X and this is sibling of next X. Again, look at here, X and this has the same degree but this is different degree. So one will be the parent of other. Since X is parent of next X, so you will move here, 12, 18 remain here, 3 and then 15 will come here because whole guy will come as a like left child of 3, right? So this is how it is done. Now x and next x, they have the same different degree. So you will move here and this will be moved here. So we are done, finished. So it is very important operation, right? So you keep watching. Thank you.